Good morning or afternoon, and welcome to the second webinar in a series of webinars that will address issues related to the seismic retrofit of unreinforced masonry buildings. My name is Nicholas Fan, and I'm the Deputy State Historic Preservation Officer for the Washington State Department of Archaeology and Historic Preservation, or the SHPO. We've partnered with the Association for Preservation Technology Northwest Chapter to bring you this series about unreinforced masonry buildings. It was originally scheduled to be an in-person event in Seattle this May, but here we are. Due to the ongoing pandemic, we're here with you virtually, and I'm glad that you're all able to join us. We're going to cover an array of topics related to URMs over the next few weeks, and to view other webinars in the series, we had one starting last week. You can go to www.dahp.wa.gov/URM symposium. We'll put a link in the chat box for you, so that you can go register for future symposia, for future webinars, as well as to view the one from last week. Just a couple of housekeeping items before we get started. If you have any questions during the webinar related to either content or the technical issue, please use the chat box or the Q&A box to send a message to us, and we'll do our best to address your question, comment, or issue. We're also happy to provide AIA credits today to those of you who have requested them. And at the conclusion of the webinar, we're going to send your AIA numbers to the AIA in order for you to receive your credit. So the AIA learning objectives today are as follows. You can read and see them for yourself. Number one is to understand how the Secretary of the Interior standards for rehabilitation are applied to historic building seismic retrofit projects. Understand how to assess different risk factors given seismic zones, existing structural systems and non-structural components, and project goals. Understand how to prioritize historic fabric and spaces when developing alternative approaches to historic building seismic retrofits, and understand how design teams for various projects approached seismic retrofit challenges given variables such as existing structural components, programming, and phasing. This webinar today is being recorded and will be available for viewing on DAP's YouTube channel within a few weeks, but if there are no glitches, unlike the one that we just had, we might be able to post the video later today. Today's presentation will explore the intersection of seismic retrofits and standardized historic preservation principles, namely the Secretary of the Interior standards for rehabilitation. With careful planning and execution, historic buildings can be successfully rehabilitated and made safe for continued use or adapted to a new use while preserving their historic character. This presentation will outline important considerations contained in Preservation Brief 41, the seismic rehabilitation of historic buildings, on how to plan and execute a historic building seismic retrofit. It's important to note that while the concepts contained in this session are imperative to apply to historic URM buildings, the concepts may also be applied to any historic building in need of seismic retrofitting, regardless of the structural system and eccentricities. In fact, the case studies we'll explore today encompass structural systems that are not exclusively URMs. Joining us today are Antonio Aguilar, Matt Alfs, Andy Phillips, and Rob Thompson. Antonio Aguilar has been with the Technical Preservation Services National Park Service headquarters in Washington, D.C. since 2000. He provides technical assistance and review for projects applying for the 20% Federal Historic Tax Credit Program for historic rehabilitation. He also contributes to the development of policies and guidance on the application and interpretation of the Secretary of the Interior standards for rehabilitation, as well as on the treatment of historic properties and materials. Among the publications he has authored is Preservation Brief 41, which you'll learn about today. He received a Bachelor of Science in Architecture and a Master of Architecture degrees from the Georgia Institute of Technology. Our second speaker, Building Works founder and principal architect Matt Alfs, designs innovative and carefully detailed buildings that contribute to the communities and clients they serve. He brings 2 decades of professional experience to the firm, specializing in the design of civic and community facilities, adaptive reuse projects, and historic preservation. Matt founded Building Work in 2016 in order to focus directly on work that supports the health of cities, the environment, and culture. Previously, he served as managing principal at Weinstein AU, where he led the design of public libraries, institutional, and commercial projects. Since 2000, Matt has served as a visiting lecturer and design studio critic with the University of Washington Department of Architecture. He currently serves on the board of directors for Seattle's ACT Theater and on the King County Library System Foundation Board. Matt earned a Master of Architecture from the University of Washington and studied architecture in Rome, Italy, and at the California College of Arts. He received his BA in art from the University of California, Santa Cruz, and is an alum of the Urban Land Institute's Center for Leadership. Our third speaker today is Andrew Phillips. Andy is an associate principal for SMR Architects in Seattle. SMR Architects has been a leader in preservation design for over 40 years. During this 25 years at SMR Architects, Andrew's experience has primarily focused on preservation as a solution for maintaining affordable housing that includes projects across the state in Seattle, Tacoma, Spokane, and Bellingham. Andrew earned a Master of Architecture from the University of Washington and his BA at Texas A&M University and studied architecture at the Royal Institute of Technology in Stockholm. He has served on the Board of Trustees for the local design journal Arcade and is founding member of the local chapter of Docomomo US, WIWA, that advocates for the appreciation and preservation of modern buildings. Rob Thompson is trained as an archaeologist and historic preservation planner. Please forgive me, Rob. I know your name. He has worked for the Presidio Trust since 2006 and currently manages the agency's historic preservation program as its federal preservation officer. Prior to the trust, Rob developed historic preservation training programs in Southeast Asia for the Getty Conservation Institute in Los Angeles. He has written extensively on historic preservation policy in the US and Asia, including a book entitled Architectural Conservation in Asia, National Experiences and Practice. He holds a bachelor's degree in archaeology from the University of Virginia and a master's degree in historic preservation from Columbia University. So obviously we have some very well-esteemed speakers to join us today, and we're going to kick it off with a talk from Antonio Aguilar with the National Park Service.
Hello. This is Antonio Aguilar. I work with the Technical Preservation Services Division of the National Park Service in Washington, D.C. TPS administers the Federal Historic Preservation Tax Incentives Program in partnership with the State Historic Preservation Offices and the Internal Revenue Service. We also maintain the Secretary of the Interior standards for the treatment of historic properties and publish educational materials on interpreting the standards and on the treatment of historic properties and materials. In this presentation today, I will start with an overview of the framework that establishes how a building is designated as historic and how the Secretary of the Interior standards for rehabilitation are applied to the seismic retrofit of historic buildings. Many historic rehabilitation certified under the Federal Historic Preservation Tax Incentives Program include seismic reinforcement and demonstrate that with careful planning and execution, seismic reinforcement can be successfully incorporated in historic rehabilitations, and how seismic code requirements can be met without significantly altering the visual qualities that are important in determining their historic significance and without losing important historic features or materials. What is a historic building? According to the International Building Code, a historic building is any of the following: one that is listed or preliminarily determined to be eligible for listing in the National Register of Historic Places, one that is determined by the Secretary of the Interior to contribute to the historic significance of a registered historic district, or a district preliminarily determined to qualify as a historic district, or one that is designated as historic under a state or local preservation program that is approved by the Department of the Interior. I started with the code definition because buildings that qualify as historic can often use alternative code compliance methods or allow the building official to make determinations without automatically imposing the requirements for new construction. In most cases, building codes with provisions for historic buildings do not allow code standards to be waived. Instead, they often allow alternative methods to achieve reasonable levels of safety. Therefore, familiarity with these codes and a good working relationship with the code The local code official is extremely important for building professionals involved in the rehabilitation of historic buildings. So what is the National Register of Historic Places? The National Register of Historic Places is the official list of the nation's historic places worthy of preservation. Authorized by the National Preservation Act of 1966, the National Park Service created and maintains the National Register of Historic Places as part of the national program to coordinate and support public and private efforts to identify, evaluate, and protect America's historic and archaeological resources. To be listed in the National Register of Historic Places, a building must be associated with significant aspects of American history, architecture, archaeology, engineering, or culture. Buildings can be individually eligible or part of a larger district. They also must possess integrity of location, design, setting, materials, workmanship, and association. Under the National Historic Preservation Act, the Secretary of the Interior is responsible for establishing professional standards and for providing guidance on the preservation of the nation's historic properties. The Secretary of the Interior standards for the treatment of historic properties apply to all projects receiving Historic Preservation Fund grant assistance and other federally assisted projects. Otherwise, these standards are intended to provide general guidance for work on any historic building. The treatment standards developed in 1992 and codified into law in 1995 address 4 separate treatments. Those are preservation, rehabilitation, restoration, and reconstruction. As mentioned before, the Secretary of the Interior standards for the treatment of historic properties are regulatory only for projects receiving federal assistance. For projects applying for the 20% tax credit, compliance with the Secretary of the Interior standards for rehabilitation is mandatory. The fundamental principles of the standards for rehabilitation are identifying, retaining, and preserving the features and materials that are important in defining the historic character of a building. The rehabilitation standards promote the continuous use of historic buildings either for their original or for a new use, and allows for alterations and additions in order to accomplish this. For this reason, identifying the features, spaces, and materials that define the historic character of a property before planning any intervention is extremely important. This information allows the owner, designer, and other professionals to understand what elements need to be retained and which can be altered, modified, or even removed. Any reference to the standards in my presentation refers to the standards for rehabilitation. The standards for rehabilitation acknowledge the need to make alterations and/or additions to a historic building in order to allow a continuous use of the building or to adapt it for a new use. As a treatment, rehabilitation is not so much about avoiding change as in restoration, but it's more about managing that change. This is especially true when it comes to seismic reinforcement. Needless to say, when choosing a new use for a building, it is important to consider whether the new use will require extensive alterations to the historic building and whether these alterations will impact the historic character of the building. When planning a seismic rehabilitation, it is important to conduct a thorough evaluation of the building. To begin, significant spaces and features that define a building's historic character should be identified. We will discuss this further in the presentation, but identifying significant historic spaces and features is necessary in order to establish where changes are appropriate and where they are not. It is also important to know how the building has changed over time. This includes not only determining what the changes are, but also evaluating whether those changes have acquired significance in their own right. Number two is what is the physical condition of the building? Everything from the structural components to the finishes need to be evaluated. If structural elements, architectural features, or materials in the building are significantly deteriorated, they may be replaced in kind or with compatible substitute materials. When replacement is appropriate, this can provide a great opportunity to strengthen the structural capacity of the building and reduce its seismic vulnerability. Number three is an evaluation of the seismic strength and vulnerabilities of the building so that it can be reduced or minimized. And lastly, it is good to evaluate how and what additional demands will be necessary in order to accommodate a new use. As I mentioned before, rehabilitating a building for a new use may require extensive alterations to the historic configuration of the building or trigger a higher seismic performance or code requirements. So what is historic character? According to the standards, historic character is the aggregate of all the features that makes a building unique and gives it its identity or its own signature. It is established by its form, size, scale, finishes, and decorative features or lack thereof. It is also influenced by the choice of materials of its architectural components and by the dimensions, detailing, color, and other surface characteristics. Detailing, geometry, size, massing, fenestration pattern, location, and articulation of its entrances, materials, and other features define the historic character of this building's exterior. Volume, architectural expression, structure, finishes, circulation patterns, and other features give buildings' interiors a distinct character which is important to preserve. Interior character-defining spaces include specifically designed functional spaces such as an auditorium, as the image on the left, or an open space on an industrial building as seen on the image on the right. Some interiors are characterized by their decorative finishes and others by the lack of them. Further information about identifying historic character is available in Preservation Brief 17. Architectural character, identifying the visual aspects of historic buildings as an aid to preserving their character, and Preservation Brief 18. Rehabilitating interiors and historic buildings, identifying and preserving character-defining elements. These publications are available on the TPS website and can also be ordered through the government printing office. The guidance in my presentation is largely taken from Preservation Brief 41, where you can find additional information on how to approach a seismic rehabilitation strategy that is in accordance with the Secretary of the Interior Standards for Rehabilitation. To put it in a single sentence, the goal of a successful seismic rehabilitation is to reduce the seismic vulnerabilities of a building while retaining historic materials and features to the greatest extent possible, and avoiding or minimizing alterations to significant historic features and spaces. The following example shows the rehabilitation of a historic church in San Francisco into an event space. This project involved the addition of two significant structural interventions. A new shear wall, shown in the location pointed by the arrow, was added to the rear of the building. Adding the new shear wall from the exterior avoided any potential alterations to the building's interior. Constructing the new shear wall from the exterior avoided removing or altering any of the architectural features and finishes in the apse. The other major intervention required additional steel reinforcement within the towers. The towers, while important architectural elements of the building, are not considered primary interior spaces, and they provide a good location for additional structural reinforcement. The strategic location of these seismic interventions avoided any significant alteration to the building's character-defining interior and exterior features. So let's look at some of the key issues to keep in mind when planning a seismic retrofit. Number one is that historic features and materials, both structural and non-structural, should be retained and not replaced wholesale in the process of a seismic strengthening program. 2 decades ago, seismic rehabilitations of unreinforced masonry buildings, such as this historic winery in California, often involve wholesale removal of the interior heavy timber framing as a common seismic retrofitting approach to these buildings. While this may have been just barely acceptable in terms of meeting their rehabilitation standards at the time, losing the original timber framing was unfortunately a significant loss of historic features and materials. A more recently completed rehabilitation of a similar winery in California took a more successful approach in terms of retaining the historic interior timber structure. In this example, rather than completely removing and replacing the historic timber structure with a new steel one, the historic structure was reinforced with additional steel plates bolted through the wood, thus allowing the historic interior timber structure to remain. Hollow clay tile is a particularly difficult building material to deal with in many historic rehabilitations, not just because of seismic concerns. Very often, complete removal of all interior hollow clay tile walls is proposed. However, in some buildings, important character-defining features and finishes are lost if the hollow clay tile is removed. When important historic features are present, the recommended approach is to reinforce the wall to preserve the historic features and finishes. When necessary, removing historic finishes on the less visible side of a wall in order to reinforce the wall and preserve the significant historic features and finishes on the more visible side is recommended. The drawings on the right show 2 reinforcement methods used on this project. The detail on the upper right shows a new steel stud wall added for reinforcement to the side of the wall that was more plainly finished in order to preserve the opposite side of the wall, which was highly ornamented. The detail on the bottom shows a section of a wall above an opening reinforced with steel rods embedded in grout in order to save the historic details and finishes. The second consideration to keep in mind is that if historic materials must be removed during a seismic retrofit, they should be replaced in kind or with compatible substitute materials. In some cases, removal of historic finishes may be necessary in order to install the new structural reinforcement and avoid altering the historic character of an important interior space. In the King Street station in Seattle, interior plaster finishes were removed in order to install steel reinforcement in the walls. Molds of the historic decorative plaster elements were made in order to reproduce and replace them after the structural work was completed. At the end of the project, most of the historic plaster finishes along the exterior walls were removed and replaced in kind. This allowed for the new structural steel to be completely hidden and avoided altering the visual character of this important interior space. The third important consideration to keep in mind is that new seismic retrofit systems should work in concert with the inherent strength of the historic structural system, and whether hidden or exposed, their installation should respect the historic character and integrity of the building. In some historic buildings, hiding the new structure may not be necessary. When the new structure does not impact significant spaces or finishes, the new structure may remain exposed as long as it does not directly impact historic architectural features such as windows or doors. Locating the new structural elements some distance away from the exterior wall greatly reduces the visual impact of the new structural reinforcement. Seismic solutions that involve significant alterations to primary character-defining spaces, such as the subdivision of this double height space, do not meet the standards. Working with the inherent strength of historic buildings can minimize the need for extensive seismic reinforcement and lessen the impact on historic character-defining features and materials. The building featured here is the Hibernia Bank in San Francisco, built in 1892. It is listed on the National Register at the national level of significance and was designated as a San Francisco Historic Landmark. It is one of the finest examples of its kind in San Francisco and one of the few structures to survive the 1906 earthquake. The building's large, open spaces on the ground floor are lavishly decorated and are important in defining the building's historic and architectural significance. Preserving the historic visual character of these important character-defining spaces and finishes was of utmost importance in planning the seismic reinforcement on this project, which was certified under the federal tax incentives program. The methods used to reinforce the exterior facade of the building involved core drilling to add steel reinforcement in some of the columns. Bond beams were added to reinforce the roof. The two large openings on the roof were identified as problematic and needed to be addressed. The location and placement of the bond beams was carefully designed in order to avoid significant alterations to the building's appearance. After the beams were placed, historic finishes and decorative elements such as the balustrade were reinstalled. To reinforce the hollow clay tile walls and other masonry walls on the interior, metal stud walls were introduced. When thickening the walls was not possible, fiberglass reinforcement was added. In the end, the careful planning of the seismic rehabilitation allowed the new reinforcement to be virtually invisible. As a result, the building's exterior remained unaltered, as well as the banking hall and other character-defining interior spaces. To conclude, I would like to stress the importance of doing a thorough evaluation and investigation of a building before planning a seismic rehabilitation. The value of putting together an experienced team cannot be underestimated. Every building is unique and requires an approach that is tailored to its physical attributes and historic character. I would also like to encourage early consultation with the State Historic Preservation Office staff. They are a great resource and can provide valuable guidance when planning a seismic retrofit program. And finally, when applying for tax credits, an applicant may request that the State Historic Preservation Office ask the National Park Service staff for a preliminary consultation to evaluate the viability of a particular seismic strategy. And finally, I would like to encourage you to visit our website for more information. And thank you for your attention.
Thank you, Antonio. And just as a reminder, we will be covering tax credits as another webinar at the end of the series. So we'll be talking about the tax credit program. And if you have any questions, it's always important to reach out to your State Historic Preservation Office, to your local preservation office in the city or jurisdiction you live in, And again, one of the points that Antonio stressed at the end is definitely to have early consultations as you're developing your schematic design for these types of projects. And it's imperative to have these conversations not only with SHPO or with any kind of approval that you might have to go through, but also with the building department. It's a really important player to have understand your project when you're developing a seismic retrofit strategy, because there's definitely no one size fits all for any of these projects. And as you'll see with the case studies, these are the types of things that will definitely vary from project to project, and there's no standardized approach, especially when you're dealing with existing and or historic buildings. So with that, I'm going to hand it over to our first case study with Matt Alfs. I'm just going to give the reins over to him.
Antonio, that was a great presentation, and I think that what I have to discuss today follows on that pretty well as a case study of our adaptive reuse preservation project for the building that we currently call Town Hall Seattle, but originally was the Fourth Church of Christ Scientist in Seattle. This first slide here, we were fortunate to have the original drawings from the architect George Foote Dunham, because this building was in ownership by the Christian Scientist Church until the late 1990s. So we had these original drawings. They're really beautiful, wonderful drawings. It's amazing how descriptive they are of the architectural character, but really lack any other detail or construction or engineering that we would normally see in a current set of drawings. So we really had to do a lot of investigation. But first, I wanted to touch briefly on this building and its relationship to Seattle. You see the building here. This is a photo from the 1920s, so shortly within the decade after the building was built. And it's really on the edge of downtown Seattle, which stretches along the waterfront, and then residential areas to the east. And this time, this was a low-rise city. Seattle was a low-rise city. You see the mid-rise downtown core still under construction, and it's an example of church buildings that there were very large church buildings throughout cities, and most of those congregations by the late 20th century had either moved to the suburbs or disappeared. So there's a need to reuse these buildings, and it's really a great challenge, I think, to find good ways to reuse them. This is a photograph of the building from the late 1930s, showing its condition. Of course, the building was designed in the classic revival style, as many of the Christian Scientist churches were. It's really a beautiful architecture, highly detailed, but yet one of the wonderful things about it for reuse is that it lacks a specific iconography. So there isn't specific religious iconography in the architecture, which really lends itself to reuse. This building, this is a photograph of after we completed the project, and you can see there's very little change to the building exterior. One of the things that's, I think, really significant about this building is that it may be one of only 2 buildings in Seattle in which the entire exterior is clad in white terracotta on all sides. Usually terracotta was used on a primary facade. The Smith Tower is one building that's clad in terracotta, and this is one of the only other ones that we're aware of. Our investigation, as Antonio described, the need to investigate how the building was built is really significant when approaching a seismic retrofit. And what we learned about this building is that it's really a hybrid building. So it was designed in 2 phases. The first phase was built in 1916. The second phase was built in 1922-23. And it was a period when construction technology and engineering was really evolving. So the building has unreinforced masonry perimeter walls. It has cast-in-place concrete construction, especially at the basement level. The second level, which is a street level, and the upper level, which is the Great Hall or auditorium, are a hybrid of URM, unreinforced masonry perimeter, structural steel. There are trusses, really amazing, huge trusses that are embedded in the walls, and then concrete, cast-in-place concrete. And so there are 3 different systems brought together to make a fairly complicated existing building. Further complicating it is a long span roof system. So the building has a vaulted roof, a cruciform vaulted roof that intersects a large center. So a real significant assembly space, significant life safety risk in a seismic event. And the building had suffered very significant damage from previous earthquakes, the 1949 earthquake and the Nisqually earthquake in 2001. Our design challenge was to convert this church, which was in its really original condition for the most part, into a state-of-the-art performing arts center. And by that, we mean patron services such as restrooms, accessibility, elevators, entirely new HVAC systems, entirely new acoustic systems, lighting systems, in a building that was never designed to have them. And then, of course, the biggest aspect of this was the seismic retrofit, because when you're doing this much renovation on a building, you are required to bring it up to code in general. So the seismic retrofit became an early focus of the design. This diagram just shows the different program elements of the building after it's completed. The next drawing shows the design challenge is that we had very little space to put new elements, new structural elements or anything else. The building, in addition to the exterior of the building having very significant historic value, but also the interior, the Great Hall and the lobby spaces on the main floor, level are all of high historic significance, and all of which needed a very sensitive approach to renovation or to the seismic retrofit. Again, working with very limited spaces for new plumbing, for piping, for new steel systems, et cetera. So approaching the seismic retrofit design, we have a great structural engineer, Magnuson Clements Associates, which is a national firm based here in Seattle. And the starting point for most seismic retrofits, or for many seismic retrofits that you might see, are introducing new braced frames or shear walls. And you know, the buildings built in this era do not have structural elements that are specifically designed to resist sideways motion or lateral forces. So we have to put those into the building. As Antoni mentioned, it's a significant challenge. This would be the sort of like the off-the-shelf sort of approach on this image right here. Steel braced frames inserted in the center of the major walls, which have vulnerability, in this case, because very large windows. We have double height walls with very large stained glass windows. Obviously, this was not an approach that we wanted to pursue, and it was not an approach that met the goals of working on a historic building like this. But I mention this because this is where you start when you're talking about engineering a building. And you would see this approach very often used in sort of warehouse buildings or other URM buildings, the big braced frame in the center of the wall. However, we went back to the drawing board and worked really close. And this is, again, what that would have done to the interior of the space. So here's the interior of the Great Hall. The brace frame approach, putting brace frames where the walls are most vulnerable, you would have had this impact, which obviously was unacceptable. But we illustrated here to sort of describe our path of finding a different approach. We went back and we looked at the building, and what we realized is that the building has stairwells in each of the four corners, which is great for exiting. But these stairwells, the finish in these stairwells was not nearly as highly finished or decorated as the finish in the main spaces. These two stairwells back here are really back of house spaces. And these two stairwells were significant, but the wall surfaces were pretty straightforward. So our structural engineer and I came up with an approach of putting in new concrete shear walls in the corner of the building and then tying them together with steel plates. And the use of steel plates, in this case, we used epoxy to secure the steel plates to the concrete slabs and connect them to new concrete shear walls in the corners of the building. There was also a need then to address these URM walls, the ones that have the big stained glass windows, and their out of plane movement. So once we addressed the stabilization, the building was no longer going to move side to side, but the big walls could still fall out. So that's where we had to put new structural steel that would be visible. Here's a diagram of the final structural design. You're seeing them in orange or this light orange color, the concrete shear walls in the corners of the building. These are 3-story high 10 to 11-inch thick concrete shear walls. In red are all new structural steel, which is concealed behind finishes or above ceilings. And then in blue is the only elements that are visible, which are the out-of-plane steel on these big, large, vulnerable walls. Here's some photos of the construction of these concrete shear walls. It's really difficult to do inside a building, but our general contractor, Raffin Construction, did a great job helping to figure out how to build this and to get it done. But it was really, really challenging. A tremendous amount of rebar that had to be put inside, and then hand pouring the concrete into that space for these 4 3-story tall shear walls in the corners. Here's a completed view on the right of one of the stairwells with the shear walls in place and all the finishes put back. And here's a view of the Great Hall with that out-of-plane steel that I described. We really went to great lengths to design this steel that had to be exposed in a way that we felt was sympathetic to the architecture. I'm about out of time, so I'm going to wrap it up here. Sympathetic to the architecture, and then again allowed it to be exposed. Finally, a couple more slides here. These images show the tremendous amount of infrastructure that had to be inserted into this building. On the left, these are all the structural systems. In the center, the new HVAC, mechanical and electrical and plumbing systems that went into the building. And then on the right, all the new theatrical and acoustics systems. Much of all this work was concealed. So to summarize our approach to the seismic retrofit of historic buildings, a few key strategies or ideas that I think are really important for any building. One, study the building and learn how it was built, what makes it unique. I think what you find when you're dealing with buildings of this age is that they're all different, and there isn't clear documentation. You really have to become sort of a forensic investigator, or you and your team do, to understand how it was built. Look for observed damage and look and wear patterns to understand weaknesses in the building. That can be done visually by architects and structural engineers. I think it's a part of getting to know the building. The project is going to require really extensive collaboration between architect, structural engineer, and other specialists. And the owner and the design team needs to be aware of that. We really need time and a great deal of effort to understand and collaborate solutions. And then there are no standard solutions. I think that sometimes there's a desire to find a quick fix, but really the right approach, if we're going to work with Secretary of Interior standards, is to be flexible and find solutions that you may not have thought of before. Of course, we have to determine the character-defining features that need to be lightly touched. And then we think it's valuable to try and create a visual dialogue between historic and new elements so that you can see and understand that difference. Last two images here. This shows the scale of the out-of-plane steel adjacent to one of the major stained glass windows in the auditorium. You can see with the figures here how big that really is. And then finally, opening night, the construction of this project took 2 years. So we were 3 years in design and 2 years in construction, a 5-year total effort by the team. And here on opening night, a chamber music performance in the Great Hall with the completed project. So I better wrap it up. I've gone over. I apologize for that, but thank you. And I will, Nick, turn it back over to you.
Sure thing, Matt. And keep your mic on because we have a quick question from the audience as we transition presenters as well. First of all, great project. I just absolutely love this project from start to finish, and everything about it, is just really well executed, in my opinion. So the question we have from the audience is coming from Sean, and he's asking, would it have been possible to use TRM or FRP instead of the concrete shear wall, or were the forces too big for an approach like that?
That is a great question. We looked at actually carbon fiber, but really the forces were too big for the weight of this building, a really incredible weight building because of its hybrid construction. And then also the design, the vulnerability of this long span steel truss overhead. There was just a lot of softness in the structure. So concrete and steel were the solutions that the structural engineer was able to do, but he did explore other alternative methods, including carbon fiber, but wasn't able to resolve the forces. We did, during construction, change the drag struts to steel with epoxy which no one on the team had done before, but there was testing done, a great deal of strength testing done throughout the building. And that steel and epoxy approach was a lighter touch than concrete drag struts, which was the initial concept. A great question.
Great, thank you, Matt. And another quick question, which I'll just answer real quick. This was not a federal historic tax credit project, although I know consideration was made, and we don't know whether it would have met the Secretary of the Interior standards reviewed by SHPO and the Park Service. I know that SHPO reviewed it as part of a grant that you received. So in our opinion, it met the standards. We don't know if the National Park Service would have certified it because it was not ultimately a tax credit project, but certainly well executed and in my opinion would have passed muster.
Thank you.
Okay, we are moving on to Rob, and I have requested him to share his screen. So we'll get that pulled up, and then we'll get to learn about some buildings at the Presidio in San Francisco from Rob Thompson.
Okay, thank you, Nick. Get sorted here. Okay, can everybody see my screen there, or my presentation?
Looks good.
Okay, great. So thank you very much to Nick and Kim and my co-panelists. My name is Rob Thompson. I'm the Federal Preservation Officer for the Presidio Trust here in San Francisco, California. As you gathered from my bio that Nick read at the top, I'm not an architect or an engineer, but I come at this issue as a preservation planner and as a preservation program manager. I'm responsible here for a large and complex and publicly held site that has a long history of seismic events, as evidenced by the historic image from 1906 on your screen now, and lots of unreinforced masonry buildings. So I'm hoping that provides a complement to my co-presenters, and away we go. So just to give you a sense of what I'm going to cover today, I want to introduce you to the Presidio of San Francisco. It's an unusual place with a long and very interesting history that I'm only going to touch on, trust me. I'm going to talk a little bit about how our historic preservation program works at the Trust and the ways that we use our tools available to approach seismic retrofit projects. And then I will touch on a handful of seismic retrofit examples in an area of the Presidio known as the main post, which is really the historic core of the park. And then, time allowing, we can get into a little bit of Q&A. So just to get you oriented, the Presidio is located at the foot of the Golden Gate Bridge in San Francisco. It's a former U.S. Army base and is currently a National Historic Landmark District. The site is managed since the Army's departure by primarily by the Presidio Trust, which is a federal agency. That's who I work for. We have about 250 employees with a variety of different functions, including an on-staff preservation team of professionals. And this includes compliance managers like me, design professionals, archaeologists, as well as tradespeople. After the Army left the Presidio in 1994 and the Trust began its work in 1996, we were given a very unusual mandate by Congress, which was to be fully financially self-sufficient by 2013. That is a goal that we accomplished, so that was met, but that mandate has informed a lot of our decisions about how we approach rehabilitation projects, whether they're URM or really anything else. The primary way that we go about our work is engaging in public-private partnerships that bring outside capital into the park to invest in our buildings and rehabilitate them to put them back into service. Nothing at the Presidio is ever bought or sold. It's all leases, long-term leases. And the money that's generated from that leasing activity goes towards supporting our preservation activities, along with natural resources conservation, recreation and interpretation of the NHLD. Again, to give you a sense of the scale of this place, it's about just under 1,500 acres. The Trust does co-manage the site with the National Park Service. There's a jurisdictional boundary whereby the Park Service has the waterfront areas, but the interior, where the vast majority of our 6 million square feet of built space is managed by the Trust. We have just over 768, we have exactly 768 buildings in the park, and about 400 of them contribute to the landmark designation. Of those 400, about 135 are unreinforced masonry buildings, and these come in a variety of shapes, sizes, and condition, all of which inform our approach to rehabilitating and retrofitting them. So because of these unique considerations, we go about planning for our rehabilitation projects in a bit of a special way. Our work is overall guided by a 2002 management plan that sets forth broad land use priorities, and we approach projects in both strategic and opportunistic ways. So in other words, outside entities can approach us unsolicited or through an RFP process to invest their money into our buildings, or we can invest our own capital funds into buildings in order to bring them back online. And we usually have around $8 to $10 million a year that's generated from our leasing to invest in new capital projects. Once rehabilitated, our buildings attract a variety of different tenants and program needs. Office use is a big one, but there's also mixed use buildings, cultural facilities such as museums, hospitality like hotels and restaurants. So we have a huge range of program considerations that go into our rehab planning. Once the rehab gets underway, we put a couple of tools that we have at our disposal into play, including a in-house Section 106 review process that's guided by a programmatic agreement we have with the Park Service and the California SHPO's office, which has been very successful and very helpful over the years. We also have our own in-house code official and permitting office that helps set standards and code considerations for our projects. As I mentioned, we have design professionals on staff, architects. We don't have an engineering team, so we do contract with outside A&E teams to bring them in to do the work, but we have professionals here on staff to guide those teams. Preservation Brief 41 is, of course, a guiding principle to all the work that we do around seismic retrofits. And then as far as code guidance, we use the International Building Code along with the International Residential Code and existing building code, along with FEMA guidance, including the National Earthquake Hazards Reduction Program, recommended seismic provisions for new buildings and other structures. And then we have been in the process of incorporating the executive order from 2011 that established a federal earthquake risk management standard. So all of this goes into the pot when we're considering how to approach a particular seismic project. But in general, our upgrades are designed to provide life safety for building occupants in the event of a major seismic event, but they are not necessarily designed to prevent full building loss. So other factors that we consider when planning and designing projects are, and a lot of this came up in my predecessor's presentations, but the integrity of the resource is a big consideration. We work with both interior integrity as well as exterior integrity. for our buildings, but there's a big variety in what the Army left behind that we take into consideration. The specified program and building user is a big factor, of course, whether a building is meant to house a museum collection versus an office use. Site-specific considerations, even though we're working in a very local environment, a lot of different factors come into play, everything from geotechnical differences and variations to differences in the actual composition of mortar used in otherwise identical seeming buildings. The approach and strategies of different A&E teams also very much comes into play. Different structural engineers in particular have different approaches to how they will do a project. And then, of course, the particular client and the budget they bring informs how things go forward. So real quickly, within my last minute here, I just want to show you a couple of quick examples of seismic retrofits here in the main post, beginning with a tax credit project. Antonio was involved in this. This is a 1909 band barracks that was rehabilitated in 2010 using a shotcrete perimeter wall solution for the basement and 2 upper floors of this masonry building. Right next door, almost identical building constructed in 1895 used a very different approach, in this case FRP, or fiber reinforced polymer, and this was used in this case due to a high level of interior integrity that this building had that we really wanted to retain and have the opportunity to retain with that particular seismic strategy. Again, just moving down a row of buildings here, this one is not fully rehabilitated, but has been stabilized in recent years using limited brace frames. But at some point, this will get a full seismic rehabilitation prior to occupancy. And then its neighbor used shotcrete perimeter walls and a pretty major interior intervention due to the fact that it's housing a museum collection, in this case, the Walt Disney Family Museum. Just down the road, and these are my last 2 examples, is a 1903 bachelor officers' quarters that was rehabilitated in 2012 as a hotel. And this used a shotcrete basement approach with center core at the porch piers that you see, the 4 porch piers you see on the front. And last but certainly not least is our oldest building. This is Building 50, our Officers Club, which was built around 1800. It's an adobe building. You saw an earlier image of it that also used center core drilling to tie in the roof membrane to new concrete footings in order to structurally reinforce the adobe sections of this building. So that is my presentation. I'll either take some questions or hand it over to Andy.
Thank you so much, Rob. Really great projects. I shared a link to the structural engineer who worked on buildings 101, 103, and 105. So that link is in the chat box so you can learn a little bit more about those. And also you can go to the Presidio's website if you're interested in learning more about the Presidio in general and some of the other undertakings. I've also shared some links from Matt's presentation on Town Hall. So there's a couple things so you can read a little bit more. And we do have just one quick question from the audience, Rob, before we hand it over to Andy for our last case studies. Yeah. And the question is, with the shotcrete, how are the interior finishes dealt with where the shotcrete was applied?
Yeah, in the case of the shotcrete, they were largely lost, with the exception of the window surrounds and a couple of other key features that were avoided by the shotcrete panels intentionally.
All right.
Take it away.
Okay. Thank you, everyone. My name is Andy Phillips. I am an architect at SMR Architects. We do a lot of affordable housing, but some commercial buildings, and I primarily do a lot of the existing buildings in the office, and I'm going to show you two case studies of buildings that we did. The Cadillac Hotel, which was rehabilitated after the Nisqually earthquake, and the Cadillac Hotel located up here at the top of the hill. This would have been a view from downtown at one time. All buildings in the forefront are gone and would be the convention center at this point. I'm going to try to, since I'm presenting two projects, I'm going to touch on mainly the primary seismic features that were put into the buildings, not as much some of the secondary ones like the veneer ties or floor-to-wall ties. So if you have any questions about that, please feel free to ask about them. Let's see. So the Cadillac Hotel is located in Pioneer Square. It was built in 1889, right after the Great Seattle Fire earlier that year. It is a 4-story building with a basement below, so counting that as one of the stories. It is individually listed on the National Register as well as being in the Pioneer Square National Historic District. Many people know about the Cadillac because it was the poster child of the Nisqually earthquake. And just to check that out, I went back and did a search just this morning, and when you put in Nisqually earthquake, you still get 4 pictures of the Cadillac Hotel. So it was severely damaged during that earthquake, and while this looks a little distressing, it also gives us some wonderful cross sections of how the building was built, and you can see the brick cross sections through the windows. The building sat unoccupied for almost 2 years as the sale of the building went to Historic Seattle continued, and then the rehabilitation didn't happen until about 3 years after the earthquake happened. The building is located at the corner of 2nd Avenue and Jackson Street in Pioneer Square. It is backed up to the adjacent Duncan building to the north. This is a ground level plan, and you can see we've inserted 3 different brace frames into the plan. The key to understanding where these brace frames got located is to know that a lot of the building was designed as core and shell. So at the time, the Klondike Gold Rush National Historic Park had not signed any leases. No offices had signed any leases. So we were basically doing the core and shell, which meant everything on the exterior was easier to insert a new structural system than it was in the interior. We could have put one along the adjacent property line, which would have made sense, but we also needed that wall to put a lot of the core elements like new toilet rooms, stairs, and egress. So this is the first floor. On the second floor, they come up again. We had mainly core and shell type office spaces. And then the portion we were trying to avoid, which is the atrium in the middle and the stair that came up from the first floor. These were the 2 major historic intact features of the building. And in this building section, you can see them. And this is a picture of the stair in a before condition. This is a picture of it after. The atrium, which had most of its historic trim, but almost none of its plaster left. Here's a picture of it after the renovation. These were the 2 primary spaces we really wanted to protect, and so it made it easier to push the brace frames to the exterior, which a structural engineer will tell you that's where they want them, is at the exterior of the building. At the elevations, you can see the one at the alley was pretty well disguised and can't be seen from the exterior. On Jackson, we located in the bay that at least had the two smaller windows at the first floor, making them a little less distinguishable from the exterior. The Second Avenue one, though, was more difficult. We had complete storefront across the first floor, and so that one became a little bit more prominent in that elevation. But in the end, it was the interior spaces that were important, so we needed to keep it there. It's hard to talk about the Cadillac without talking about the masonry restoration. This is the picture from earlier of its lost corner, which is this section here. All of the grayed out brick was either gone or had fallen, or we had to remove in order to get back to a sound masonry. But we were able to rebuild it. Most of the brick that was used, or most of the original brick after it had fallen, was damaged. So we had to find some solutions to use less brick. And so we did put the behind the veneer of the upper stories is a concrete block, which also helped in the seismic retrofit because we were able to reinforce that. So the parapets above are even stronger. We also had to locate some new brick, which we did not have a problem finding color-wise, but all the existing brick in the building had a very unusual size, both height and depth, and ended up having to use paver brick because none of the actual veneer brick matched any of the sizes on the building. So there is the rebuilt corner. The second project is the Cambridge Hotel. It was Cambridge Apartment Hotel. I'll explain in a minute. It's only a few blocks from Town Hall, which I believe is over here. The green is where I-5 went in, so it barely missed destruction from I-5 and the convention center. It was built in 1923. It is a 10-story building. It is on the National Register of Historic Places. And one of the important aspects of this project was we did have 40 tenants living in the building while we did the construction. There's 150 apartments, but 40 tenants decided to remain, so we were doing this building occupied. Now this is not a URM, but it's a concrete building, cast in place concrete, as you can see from this cover of a 1922 Pacific Engineer and Builder magazine. And it's an L-shaped building, which is, while it's a common thing for apartment buildings in order to get light courts in the middle, it's considered a unusual, not an unusual, but an irregular shape for structural engineers, because when the ground motion happens, both of the wings want to react in a different way, which is what this diagram is showing. So, and you put that into a plan for the Cambridge, that kind of action wants to make a building like this crack right down the middle of the corner. This is made even worse by the fact that the typical place to put elevators and stairs, which is right in the middle of the building, is weakening that corner even more by putting a hole all the way down the slabs of all the stories. So to understand this building a little better, it's nice to have this diagram, which here's the L shape of the building with the apartments. We have 8 stories of that. But then at the bottom, we have 2 very small floors. That the reason for that is this building is nestled nicely into a hillside, First Hill, with Union Street being an actual staircase. And and the main entry being right down there at the bottom. So it has a very small footprint at the actual bottom. And the main interior spaces that we wanted to protect were the lobby. This building was considered, as you can see by this postcard, an apartment hotel, which at the time meant it was designed for people who wanted longer stays than a hotel, but shorter stays than an apartment. And the result of that was then, besides a lobby, they also had some kind of food service type room, which this one had a tea room that was still intact, but being used as a manager's unit at the time, and a radio room that was nestled right below the tea room off the lobby. The radio room was kind of the equivalent of an apartment building providing free Wi-Fi at the time. So in order to come up with the seismic solution here, we went with concrete shear walls because it presented, we could get less of them in than we would have with steel. But we needed to avoid the lobby at the base. We needed to avoid the tea room and the radio room, which were right below. We also needed to avoid the corridors for two reasons. They were a very intact space historically, but they also needed to remain as egress throughout the project because we had 40 people still living in the building. So the concrete shear walls then went more interior of the building instead of pushing it to the exterior. The best place for any kind of retrofit would have been on the exterior corner, basically right where the lobby was located. So instead, we went with these concrete shear walls in the interior of it. And in order to protect the corridors, we braced the plaster walls. This allowed, as you can see, some egress to still get past them while they were pouring the concrete inside the unit being renovated as well. And there's a picture of the final corridor. So we managed to be able to save all the plaster and the wood trim. And since the shear walls then avoided any of the primary spaces at the ground, we were able to renovate the lobby and the radio room. This is a before picture of the lobby. There is a major column right here behind this wall. They had inserted a unit into half the lobby at one time. So we exposed that and built a new office in that location. And because we didn't have to do anything in the lobby, we managed to save the ceramic tile floor, most of the ceiling decoration, and the marble that was on all the columns. Renovated elevator. This is also part of the lobby, and then the bottom photo is what was the radio room. To wrap up, I just have a few extra photos just to show some of the other aspects of these projects. As I said, the Cambridge was a occupied building. So between that and the concrete shear walls, it made for a very unusual construction schedule. So a lot of the times they were still building concrete walls in completely renovated units. And on the right of this photo, you can see the kitchen is almost complete, but the concrete shear wall has not. And then this series of photos for the Cadillac. It sat for this way for almost 2 years in a containment frame to protect any additional falling masonry. As construction started, the frame slowly came down and the scaffolding went up. And then it entered its marshmallow phase. And when that came down, you have the restored building. Thank you.
Thank you so much, Andy. I've never seen that picture of the marshmallow or of the temporary bracing surrounding the Cadillac. So thank you. Both of these projects were, in fact, certified historic tax credit projects. That question came in at the very end of the presentation. So we are a little bit over time, so I'm going to wrap it up by saying that we have 4 more webinars left in the series, 2 next week, one on Wednesday, November 18th, and another the next day on Thursday, November 19th. If you go to our website, www.dap.wa.gov/URM symposium, you can register for future webinars in the series. And you are also able to view recordings of previous webinars as well. All webinars will start at the same time, 10:30 a.m. Pacific, 1:30 p.m. Eastern, and I hope to see you again. Thank you all for coming.